2 kilometres of rock fell out of the sky and punched a 31-kilometre hole into what is now northern Greenland. Today that scar lies hidden beneath nearly a kilometre of ice at the edge of the Hiawatha impact structure, buried under the flowing margin of the Greenland Ice Sheet. Radar sees it, meltwater rivers drain it, shocked quartz whispers its origin, but the crater itself is invisible, entombed in silence, as if the planet tried to forget the day it was struck. The hole is about 31 kilometres wide, large enough to swallow a major city. Its rim is raised, its floor subtly uplifted in the centre, and its shape is unmistakably circular. You don't get that geometry from glaciers or volcanism, you get it from something arriving very fast, carrying an absurd amount of kinetic energy. To make a crater that size, the impactor had to be enormous. Scaling laws suggest an iron asteroid, roughly 1.5 to 2 kilometres across, travelling at around 17 kilometres per second. That's 60,000 kilometres per hour. At that velocity, the asteroid's mass barely matters. The energy release is comparable to millions of nuclear bombs detonating at once. The bedrock beneath northern Greenland would not have had time to react. It would have vaporised, melted, fractured and rebounded in seconds. But here's the twist that makes this story better than it first appears. For a few years after its discovery, scientists wondered whether this was a young impact, maybe even one that struck through an existing ice sheet during the last ice age. The crater's relatively fresh morphology and disturbed basal ice made it tempting to imagine a dramatic collision into kilometres of ice, perhaps even linked to abrupt climate shifts. Then radiometric dating told a different story. The impact didn't happen during the last ice age. It didn't happen during the age of humans. It didn't even happen during the age of mammoths. It happened about 58 million years ago. That places it in the Paleocene, long before Greenland was wrapped in permanent ice. In fact, Greenland at the time of impact was nothing like the frozen landmass we picture today. It was warmer, significantly warmer. Fossil evidence from the high Arctic shows that forests once extended to extreme northern latitudes. Conifers grew there, rivers flowed across vegetated terrain. There were wetlands, lakes and soil systems, not glaciers grinding across bare rock. So when the asteroid arrived, it did not slam into an ice sheet, it hit a forested landscape. Picture that for a moment. A temperate to warm high latitude environment with conifer stands and river systems cutting across crystalline bedrock. Beneath that surface lay ancient Precambrian gneisses, rocks already billions of years old. Then a 2 kilometre iron asteroid appears in the sky. The atmospheric entry would have been blinding. At that size and velocity, the object would not disintegrate in the upper atmosphere. It would punch through, generating an immense fireball. As it struck, temperatures exceeded several thousand degrees. The iron projectile and surrounding rock instantly melted and partially vaporized. Shockwaves travelled outward, fracturing quartz grains and producing planar deformation features, microscopic scars that we still find today in sediments draining the crater. Within seconds, a transient cavity far deeper than the final crater opened in the crust. The walls collapsed inward. The central floor rebounded upward in elastic response, forming a subdued central uplift. Molten rock pulled. Ejecta blasted outward across the surrounding landscape. The final crater, 31 kilometres across, was left as a permanent modification of Earth's crust. Now the question that always follows a large impact is, did it change the world? A 2 kilometre iron asteroid is not a dinosaur killer. That role belongs to the 10 kilometre impactor that formed the Chicxulub crater 66 million years ago. But that doesn't mean Hiawatha was minor. An impact of this scale would have caused devastating regional effects. Forests within hundreds of kilometres would have been flattened or incinerated. Shockwaves would have triggered earthquakes. Ejecta blankets would have buried nearby ecosystems. Atmospheric dust and aerosols would have been injected into the sky. Whether those effects reach global significance is more uncertain. Some models suggest that an impact of this size could eject enough dust and vaporized material into the stratosphere to cause short-term cooling, perhaps years of climatic perturbation. But we don't see an obvious, globally recognized extinction pulse at 58 million years ago tied directly to this crater. If it caused global disruption, it was likely temporary. Regional devastation, yes. Planetary catastrophe? Probably not. Still, context matters. The Paleocene was already a dynamic climatic interval. Earth was in a greenhouse state. And not long after this impact, the planet experienced one of the most dramatic warming events in its history, the Paleocene-Eocene thermal maximum. There is no evidence linking Hiawatha to that event, but it does remind us that Earth systems at the time were sensitive and evolving. Back at the crater itself, the story doesn't end with impact. One of the most intriguing features found in sediments draining the structure is the presence of unusual microspherulitic melt grains and zeolite minerals like mortonite. These minerals tell us that after the impact, water interacted with hot melt material at elevated temperatures. The crater likely filled with water relatively quickly, not in the way a submarine impact would, but perhaps via rivers, lakes, or groundwater infiltration. In other words, the crater may have briefly become a hydrothermal system. Impact heat can persist underground for thousands of years in structures this size. Circulating water would have altered melt glasses, formed secondary minerals, and possibly even created habitable microclimates. Impact craters are increasingly recognised as potential temporary niches for life because of this hydrothermal activity. Over tens of millions of years, erosion softened the crater's morphology. Sediments may have accumulated and been removed. Tectonics remained relatively quiet in this part of Greenland, allowing the structure to survive without being destroyed by mountain building. And then, much later, only in the last few million years, Greenland began to freeze. As global temperatures cooled in the late Cenozoic, ice sheets expanded in the northern hemisphere. Eventually, the Greenland Ice Sheet formed and thickened, flowing across the landscape and burying the ancient crater. Glacial ice smoothed and modified the topography above it, but did not erase the deeper bedrock depression. The irony is almost poetic. A catastrophic impact that once vaporized rock is now hidden beneath slow-moving ice. The crater was only discovered because airborne radar surveys mapped the bedrock beneath the glacier. Instead of seeing a smooth subglacial valley, researchers noticed a near-perfect circle, a bowl with a raised rim. Rivers draining from beneath the glacier carried shocked quartz and impact melt fragments downstream, confirming its violent origin. The freshness of the structure made some scientists suspect it might be geologically young, perhaps even tied to the Younger Dryas cooling event around 12,800 years ago. But detailed dating of melt materials ultimately anchored the impact firmly in deep time, 58 million years. That number changes everything. It means Greenland at impact was green. It means no kilometre-thick ice sheet muted the explosion. It means forests stood where ice now flows. It means that this scar in the Earth's crust has witnessed massive climatic shifts, from greenhouse world to icehouse planet. If you flew over northwest Greenland today, you'd see white. Endless white. Nothing about the surface hints at a 31-kilometre crater below. But beneath that ice lies the frozen memory of a day when a 2-kilometre iron asteroid ended its journey and altered a forested Arctic landscape forever. Few people know about it, fewer still appreciate its scale. It's one of the largest known impact craters on Earth, and the only confirmed one hidden beneath an active ice sheet. Its discovery reshaped discussions about impact frequency, glacial modification of craters, and even the possibility of impacts into ice-covered terrains elsewhere in the solar system. Because if a crater that size can hide under Greenland for 58 million years, how many others lie concealed under ice on Earth? That's the broader geological consequence here. Hiawatha isn't just a scar from the past. It's a demonstration that the surface record is incomplete. Ice can hide violence, time can soften catastrophe, and a planet keeps secrets until technology, radar, geochemistry, isotopes, forces them into view. Somewhere under a kilometre of moving ice, that central uplift still rises gently from the crater floor. Melt-altered minerals still record the cooling of once liquid rock. Shocked quartz grains still carry microscopic evidence of unimaginable pressure. And above it all, glaciers flow quietly, as if nothing ever happened. But 58 million years ago, Greenland burned. I hope you found this as interesting as I did, and as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.